Okay, so let's look at this function. So we've got a rational function. If we're looking at the ends, so we're looking at the ends now. Grab a different pen. Okay, and since it's rational, we know this function behaves like 2x squared over x squared, which is equal to 2. So we know both these limits are 2. And the new thing is that if at the ends the limit is a constant, we know we've got a horizontal asymptote. A horizontal asymptote. And we know that's the line y equals 2. Okay, now we're going to look at the more interesting spots. So what we want to do is let's take this function. Let's actually see if we can change its format a little bit. So the thing we're going to try now is we're going to factor it. So this is be a 2x and an x, and I think if we use +1 and +1, that'll work. And the bottom is difference of squares. Oops. Not too low. That would be x plus 1, x minus 1. So this is exactly the same as the function. And what we're hoping is that something's going to reduce out. So let me grab a different pen. And I think in this function, we're lucky. And these function reduces. So we know that the function is about equal to 2x plus 1 over x minus 1. And I've never found a good name for that, but I'm going to just call that's the reduced function. We've done something with the function to make it be almost identical, except it has a little different domain. And now we're hoping that we can use that reduced function to come up with a limit. Okay, so we're going 1 plus. So let's just imagine we plugged into the reduced function. And the only time we really care and we have to use the pluses or minuses now is if we're going to get a 0. Otherwise, we're going to assume that it's essentially the number. So 2 times 1 is 2 plus 1. Okay, if we're putting in a little number that's like 1 plus, so maybe think like 1.001. So when you put it in the denominator, you would have this number that's super close to 0, but a little bit positive. So you know this function is behaving like 3 over 0 plus. And that's one of our basic forms. It's a positive number, and it's exploding up. So that is going to plus infinity. Now, if we did it from the other side, we would have 3. And if we're going at 1 from the negative side, you're thinking, oh, it's like 0.999, something like that. And so when you subtract 1 from that, you get something close to 0, but it's negative. And you're like, uh-oh, I got a plus number over a negative number. So I know this is a negative number, but it's going to explode. So this is negative infinity. And we can't say that this has a limit. And in fact, some books will even tell you that these limits don't exist if they're infinity. But for us, we're kind of thinking about behavior. So I think it's going to be helpful to use this notation. Okay, so what does that just tell you about the function? As you approach 1 from the right, the function is going to explode up. And if you approach 1 from the left, the function is going to explode down. So this time, we say we have a vertical asymptote. Because at a value, the function's exploding up or down. And so that vertical asymptote is at x equals 1. Okay, let's look at the third special number. That's when we're approaching -1. And so we're going to do the same thing. We're going to say, okay, we look at the reduced function and we're going to put a -1 in. So we'd have -2 plus 1, and we'd have -1 minus 1. And this gives me -1 over -2, which I think is a half. And so this limit is a half. And because when we look at the reduced function, like this function is for all practical purposes behaving like 2x plus 1, x minus 1. This -1 doesn't do anything special. The -1 makes makes the output of the reduced function exist. So I know this limit is the same, which means the limit is the same from both sides. So we can just talk about the limit at -1. And we talked about that a little bit in a previous lesson, but we say that this has a, and this is the new word for you, removable discontinuity at x equals -1. I think probably last year you called it a hole, but it's not really the calculus term. So you would think the graph is going to, at -1, have an output of 1/2, but there's just no output there. All right.